Alright, in this video we're going to talk about the photoelectric effect. If you need a second to write down the 4 learning outcomes, please do so at that time. Otherwise, I'm going to assume you've got the notes handy with the script under the notes pages, and let's begin. In some experiments, light behaves like a wave, but in other experiments, light behaves like a stream of tiny particles. One experiment that lends credibility to the idea that light is a particle involves shining a beam of light onto a metal surface in a vacuum. If the light exceeds a minimum energy threshold, electrons will be ejected as shown here. This is called the photoelectric effect. Shining a higher frequency light does not cause more electrons to be ejected, but those that do leave the surface will do so with greater speed or kinetic energy. Keeping the same frequency of light, but adjusting it to a brighter light, recall this means that we have higher amplitude waves, will cause more electrons to be ejected. That's the wave theory of light, but it didn't explain the entire photoelectric effect. For this, we have to turn to Einstein's Nobel Prize work from 1921. Einstein proposed that light behaves as tiny individual packets of energy. If this packet of light has enough energy, it will knock electrons out of the metal. If you increase the brightness of the light, Einstein suggested that you were increasing the number of light packets, which increases the number of electrons ejected. Building off of the equation E equals h nu, we can quantify the energy needed to eject an electron. The work function, phi, is defined as the minimum energy needed to remove an electron from the surface of a metal in a vacuum. Each metal will have its own value for phi, and this is a number you'll either be given so that you can calculate the wavelength or frequency, or you'll be given a wavelength or frequency and be asked to calculate the work function. Let's look at an example. So here we're actually asked 2 questions. Given that sodium metal has a work function equal to 3.78 times 10 to the negative 19th joules, we're asked to find the minimum frequency of light needed to remove a surface electron and to calculate the wavelength of this light. Since we're solving for the frequency, nu, we're rearranging the equation and plug in the given values for phi and Planck's constant. This gives us a frequency of 5.7 times 10 to the 14th hertz. Next, we'll take this value to the next slide to solve for wavelength. Using C equals lambda times nu, we rearrange to solve for the wavelength lambda. We get a value in meters, but it's customary to report the wavelengths for visible light in nanometers. So let's do that conversion next. Again, the textbook is demonstrating what I like to think of as the blue method for unit conversions, where the smaller unit gets the big positive exponent on the power of 10 to do the conversion. If you learned a different way and that works for you, please keep using that method. Our final answer here is 526 nanometers. Now remember on the second slide that I said shining a higher energy or higher frequency light does not cause more electrons to be ejected, but those that do leave the surface will do so with greater kinetic energy? We can calculate how much kinetic energy by using the equation Ke equals Planck's constant times frequency minus the work function for the metal in question. Let's look at an example problem showing how this works. We're asked to calculate the kinetic energy of an electron that is ejected when one blue photon with a wavelength of 472 nanometers strikes a strontium metal surface in a vacuum. To make this work, we need to decide how to apply the equations we've learned so far. We know we need the kinetic energy equation, but how do we go from wavelength to frequency? Since we need h times nu to plug into our kinetic energy equation, we can use the relationship E equals h times nu to get the value we need. We can also incorporate nu equals c over lambda to knock this out in one big calculation step. Finally, we can use our kinetic energy equation to find out how much of the photon's energy is left over after the electron is liberated from the strontium surface. We see that the amount is small, but equals 6 times 10 to the negative 21st joules. Note that we lose two significant figures in the process of doing this calculation.